Physics Essentials, video 45. It's on calculating the gravitational force. We all know that there's a force of gravity holding us to the planet, but an easy question might be, why don't you experience that when you're in space? Why are you weightless? Some students will tell me it's because there's no gravity there, but we know that's true because the moon is held around the Earth and we're held around the sun. There's got to be gravity out there. And so Newton explained this years ago. And so think about it like this. Imagine that we've got the Earth and we build a giant mountain on it, and then we put a cannon at the top of that mountain. And we launch a cannonball out at the horizontal. What's going to happen? Well, it's going to fall to Earth. There's a gravitational force between the cannonball and the Earth, and so it's going to follow this nice path. Let's say we launch it faster. What's going to happen? It's still going to fall to Earth. We still have that force towards the center of both objects. Let's say we launch it faster. It's still going to fall to Earth, but if we launch it fast enough, what's going to happen? It's going to fall towards Earth, but it just keeps missing it. And so it's going to orbit around the Earth. This is how satellites work, and Newton predicted this years ago. And so what would it feel like to be inside that cannonball? Well, you would feel weightless. It's not that there's no gravitational force there. It's just as big as it was before. It's just that as you fall towards Earth, you keep missing it. And so, again, Newton's law of universal gravitation allows us to not only understand this, but to quantify it, to come up with a value for that. And we're going to do that in this video. So if we have two masses, there's going to be a gravitational force between the two. And that's always going to be attractive with anything in mass. Let's just assume that these are spherically symmetrical objects. The equation is really, really simple. It's simply the force is equal to big G, and we'll get to that in a second, times the mass of the two objects divided by the square of the distance between the two. So you simply calculate the force by multiplying the masses times this constant, and then you divide it by the center-center distance, but you're going to square that value. Center-center distance is always going to go to the center of those two objects, or the center of mass. Now on our planet, the Earth is so big in relation to us that this gravitational force, or this gravitational acceleration, we'll call it G, is essentially constant. Changes in our distance from the Earth are so small, and the mass is so big in relation to our mass, that it really doesn't change much over time. And so here's our equation. If we have two objects, then the force is going to be equal between the two, and it's explained using this equation right here, where G, we'll refer to it as big G, is a constant, and it's worth memorizing. It's 6.67 times 10 to the negative 11th. And so what else do we have in this equation? It's the mass of the two objects and then the center-center distance. And there's a nice PHET simulation that gets at that. So if I have two objects like this, and I increase the mass on one, you can see the force is increasing on both of them, and the force is always going to be equal. Now if we show the values, you'll see that those numbers are incredibly small. But what happens as we move them close to each other? The force gets larger. As we move them apart, it gets smaller. And we can start to do some actual analysis here. If we make both of their masses 1 to make the numbers easy, and then we move them 1 meter apart, you start to see that gravitational constant come out. It's a really small value. What happens now if we increase the mass tenfold? So if I increase this to 10 kilograms, you can see the force increases by 10. What if I increase this mass by 10? We also see a tenfold increase. But it's not the same if we're looking at the distance. If I double that, we're not just cutting it in half, we're taking it in by a fourth. And that's because we're squaring that distance between the two. And so if this is our equation, let me show you how to solve a simple problem. And this is what you might see in a physics class. Calculate the gravitational force between two 3.0 kilogram masses that are 2.0 meters apart. And so this is going to be, really small value, hopefully, when you get it. And so we know the gravitational constant is 6.67 times 10 to the negative 11th. I'm given the masses and the center-center distance, and so it's really easy to solve that. I've got my constant G. Then I'm going to multiply my two masses on the top, and then divide that by my center-center distance squared. And so if I simplify that a little bit, my constant is here. What happened to these units? Well, you can see that I've got kilograms squared on the top, kilograms squared on the bottom here. So those cancel. Meter squared on the bottom, meter squared on the top. And this is simply 9 divided by 4, which is 2.25. And so what's going to be my force? 1.5 times 10 to the negative 10th newtons. So it's an incredibly small value. Let me give you a problem that I'd like you to answer. So calculate the gravitational force acting on me standing on the surface of the moon. And so if you're given a problem like this, what do you have to figure out? Well, the gravitational constant is going to be constant, so you already know that. But what else do you need to know? You need to know the mass of the moon and the mass of me. And so the mass of the moon is a really large number, and the mass of me is large, but not that large. What else do we need to know? The center distance. And that's going to be the distance from the center of the moon to the surface where I'm standing. And so what you should do is use this universal law of gravitation to calculate what that force is. I'll put it down below in the video description so you can figure that out. And if you know anything about Newton's second law of motion, you could simply divide that force by the mass and it's going to give you the acceleration. And it should be a sixth of what it is on our planet. Now what's interesting about our planet is that the mass of the Earth is so big and the distance is so large that in this narrow band on the surface of the Earth it really doesn't change that much. And so did you learn to use Newton's law of gravitation to calculate the gravitational force between two objects? It's pretty straightforward. Remember, gravity doesn't go away when you're circling the Earth, and I hope that was helpful.